Yeah, this is this is last part, the part number 3 of the mega class. Yeah, let's move to the autoencoder. Yes. Okay, the autoencoder. Yeah, originally they are used to represent the entire network. It could be the image, it could be the voice, it could be the temporal data, or any pattern, or any signal or code modality of the data's resources. So there's a two. There's a elementary autoencoder, or the convolutional autoencoder, or variational autoencoder. So in this class, you're going to learn how to reconstruct uh, the different sources of data, including the temporal data, image. No, we don't want you to try to construct a video. So actually, even though it can be, it is capable, and also perform the noise removing as a filter, is known as it also acts as unsupervised learning. Yeah. So there's a CAE and VAE variational autoencoder. So that will be as a homework given to everybody to random pick a picture or doggy or kitty. So try to use a variational autoencoder to augment or reproduce the data. It is a probabilistic generation. Very interesting. So autoencoder for unsupervised learning, there's a three different capability, or it has a three different purposes. It can perform the task of feature extraction. It can perform the denoising if the original data is noising, or there's a subjective, some color, or some missing value, or yeah, they can perform the padding or stitching in the local area if the resolution is not uniform. And image and time series data reconstruction. So you can see that this is the topology of autoencoder. Input X, in between is called a code, or called a latent space or latent layer. Z, the size should be much smaller compared to the input. So from the X to Z, as known as the infrastructure of the encoder. So it's known as the downsampling. I use a convolution to shrink the size. And then the Z can be is considered the most important feature in order to represent the entire structure and the essence and content of the original input data. And then we start from Z, we like to return back to this original size called the X prime, called the upsampling. Upsampling, so it's a feature to use a larger size to perform the modification. So it's known as a decoder. So autoencoder structure, encoder F, this is a convolution plus the downsampling network. So every time we traverse the kernel from the left to right, from top to bottom, all over the entire image, and perform the downsampling procedure. Then to the Z, or the decoding, the deconvolution, and like inflate the latent layer back to the original size, so-called assembling network. So F is X down to Z. The axis is the high dimensional input row vector, or you can consider it a row vector or column vector. Then to X, and the Z transform back to the H prime. Then objective is argument of the minimization of the Euclidean distance. Euclidean distance between the X and X prime. X is the original input. H prime is a reconstructed input subject to the F and G. So it depends on what the structure, how many parameterization, and to use do the inference or do the sampling probability. So train the encoder F and the decoder so that we wish the X prime resemble X as closely as possible. So for NLP-based autoencoder, the multi-layer perceptron with a vector value only for the regression prediction. They are used for dimension reduction. So we like to call the important feature from among the abundant feature of the original data. So they use for dimension reduction. Dimension reduction still has several quite effective and very well-known techniques, such as the principal component analysis (PCA). So we just reduce the high-dimensional data into the different axes. They are orthogonal each other and perpendicular to each other. Based on the eigenvalue and the eigenvector projection. They are independent, so the kurtosis should be maximized. Then LDA is another one, linear discriminant analysis. And in the most recent in the past decade, there's another one called TSNE, TSNE, the T distribution and the stochastic neighborhood embedding. So the dimensional reduction, the Z is a latent vector, should be belong to the Euclidean space with the dimensionality P. X is a Euclidean. This is original dimensional D. The P much smaller than D. So they can also be used for entity embedding. Entity embedding sometimes that is used to decode the input variable. The input label, which is original categorical, in order to enhance the data interpretation of the machine learning model. So used for convert the high-dimensional one-hot encoding to low-dimensional real number called a label encoding. No, this is not label. This is the real encoding from the high-dimensional one-hot to low-dimensional real number. So I use it as a back-end of line semiconductor packaging process. So going to testing the process, the entity embedding just provide good a good modeling capability. And also the missing value, can be handled quite well. The Maxwell autoencoder. So we just, for example, in practice, so the data collect to the sensor enabling technology. However, sensor can be weird, or the sensor can be malfunction during some particular condition. So the data received might not be complete, which might not complete. So mask autoencoder by setting feature with a missing value or even zero, or set up or black or white. So the reconstruction capability can be reconfirmed by using the denoising autoencoder. A simple example of an autoencoder model. Assume one hidden layer in and only one encoder and decoder takes input x belong to the Euclidean distance RD, this input, and map the x into encode z is latent space R, Euclidean space of the P is a much much smaller than D. So Z can be the transformation sigma 1, the WE times X plus B. B is the noise vector as before in the CNN. So X WE encoder, and as long as the Z can be found by the nonlinear programming techniques, and as an input of the sigma 2 is decoding, decoding, transform back. So due to the Z and to the weight of the WD, D is the decoding, plus the arrow vector B prime. So sigma is element to element, or called the element-wise activation function. It's quite big one. This is like a portmanteau of the W, or portmanteau of the weighting factor, such as a sigmoid, or the ReLU or GALU. Then we train this typo. It should be TRAIN, no E. Train the input parameter, the training parameter W in encoder, and also the parameter in decoder. And the encoder will have arrow parameter B, and the decoder will have arrow parameter B prime to minimize the entire reconstruction error. So it's sum square of error reconstruction. So which can be represented the L, X, and the X prime, and equal to the Euclidean distance. So since if it's a picture, it's a 512 by 512, so going to be the one-dimensional row vector. So original and the subtract and reconstruction row vector, we evaluate the square error. So or the arrow can be the arrow vector times the arrow transpose times the arrow, the inner space, that is the square distance. So equal to the square distance x minus the sigma 2 decoder of the input WD. Z equal to the sigma 1 WE encoder x plus B, and plus the arrow vector B prime in the decoder structure. So the code Z provide a complex representation. The reconstruction procedure can be done satisfactorily due to some. You just evaluate the error, which can be validated if confirmed some assumption. You follow the bell shape, normal distribution. The fluctuation should be randomly independent, and should be uncorrelated and within a very small range. So the code Z, the coding vector, provide a complex representation of the input X. So based upon the unsupervised learning and within the data, some pertinent or most lim lim limchin key to the original data can be found. So the Z can be extract those, so we identify so what kind of the Z as a feature extraction. Then any if the set has been determined as a feature, important feature, so any common instant can be input into the autoencoder, and the Z1, Z2 can be directly obtained. Then that used for the supervised learning for classification. So this is another beauty by using the autoencoder. So autoencoder, the unsupervised learning in conventional neural networks is employed via autoencoders. So the unsupervised learning. The autoencoder structure consists of two layers, one encoding and the other a decoding layer. And the goal of an autoencoder is to achieve the identity function. So we also want, in order to avoid there's an invalid training result. Always the input times the identity is still equal to the output. So the decoding and the encoding structure is useless and in vain. And so within its whole structure, in more detail, the input of size is represented as m by n number of parameters, and within each input encoding and the output layer, aim to recreate the original input of the size p from the size the D representation. This is the decoding. So yeah, as I represent previously, encoding to RD to RP, the X to F of X. P is a number of the important feature dimensionality of the feature, important feature, and RP back to RD, and minimize the loss. So this figure is a neuron structure of an NLP base. The autoencoder, remember, is only good for the real number of time series data. It's not good for the image data. Or well, you don't. It's not necessary for you to use the NLP. Instead, the NLP can be replaced by LSTM or an N layer. So input layer, the bottle, neck, hidden layer, and all layers are fully connected, but not drawn. Okay, they're fully connected. And the output layer, reconstruction of the input layer. Actually, but what do not know, so they are fully connected. So there's a slide before I end this session. So this is a basic functionality of a CNN autoencoder. If input is a test instance in the MNIST data set, original input tool, encoding CNN. So we like to use the downsampling to the complex representation of some image like 2. Some important feature, and then decoding. We wish the decoder can, based upon the important feature that embed into the compressed representation, and can be upsampling back to the original input as closely as possible. It's known as a reconstructed input. Okay, I stop here. I hope is that clear for you. Most of you may not know um, the detail about the autoencoder. However, so autoencoder is quite effective to perform the task or assignment of the data augmentation. Then once while you have done the homework number 2, you understand. And the other generated model is known as GAN, generated adversarial model, is also good for that. However, this is well suited to the generation and the data augmentation of the image data. So thank you very much. I see you then.